Hi, my name is Zoe Yiournas. I'm a rising senior at the University of Delaware, partaking in the UD Envision summer internship program. I have had the pleasure of working alongside Dr. Beltran at the Amman Peninsula building to measure the effects of abscisic acid, also known as ABA, on leaf angle modulation in both Arabidopsis and tomato plants, particularly microtom, which I pictured here in a time lapse for reference. To give a brief overview, abscisic acid is a plant hormone that plays a crucial role in various developmental and stress-related processes, particularly in regulating seed dormancy and stomatal closure. It is also involved in responses to abiotic stresses such as drought and cold. The main objectives of my project specifically are to determine how exogenous ABA influences leaf angle in Arabidopsis and tomato, and to compare species-specific responses to ABA treatment and leaf orientation, as well as understanding potential physiological mechanisms behind ABA-induced leaf angle changes. Pictured here is me creating the mixtures of ABA, my positive control, and DMSO, my negative control, which is a versatile and frequently used solvent within the biotechnology world. It is expected to have no effect on the plants comparatively to ABA. The next step within my process is to spray the solutions I created of DMSO and ABA of varying concentrations on my replicates to measure the architectural and thermal effects that it has on the plant. The main hypothesis in my research is that exogenous ABA, in this case sprayed on the plant, will alter leaf angle by modulating cell expansion within the petiole, as well as increase the overall temperature within the plant by stomatal closure, as mentioned previously. The next step within my process, as well as a key source of where my data comes from, is side view photos of the plants, consisting of photos from before application, 4 hours after application, and 24 hours after application. This is super important for me and allows for me to go back and observe the physical and architectural changes that occur in the plant after an ABA application. Here in this photo, I have highlighted various leaves that show physical changes after the ABA application, indicating that it had an effect on the plant. The next step, after observing the visible architectural differences within the plant, is to quantitatively measure the angle changes through an external software. In this case, I used Anglemeter. Given the side-by-side photos of various times within the application process, it makes it a lot easier to compare the different angle measurements over time. Primarily within the top photo, it is easy to see that the angle increased over time within a 24-hour period, indicating that the plant did in fact expand horizontally. While this is just the beginning of this research, and there are no definitive conclusions yet, it is still promising within the world of agricultural sciences, particularly crop science. While the primary focus of the video thus far has been on the microtom variety of tomato plants, I also included data on Arabidopsis plants that I started from sterilized seed to petri dish culture to then transplanting into potting soil. Arabidopsis thaliana, commonly known as stale crest, is a widely used model organism in plant biology due to its small genome, short life cycle, ease of cultivation, and abundant seed production. While I conducted the same exogenous ABA application within the Arabidopsis plants, it has been super interesting to observe the species-specific responses to the ABA applications. While I have not yet completed the angle modulation data within the Arabidopsis plants, I have also included other data, including thermal readings for both tomato and Arabidopsis plants. Labeled here, I have the DMSO negative controls on the left side, and the varying concentrations to the right. This is exactly what one would predict to see, as higher ABA concentrations will lead to higher temperature readings. As this is still a relatively new research avenue within biotechnology and crop science, it is still exciting and promising research. But what is the why? Why is this important? As farmers all around the world constantly try to maximize their yield potential, I think that it is super important to have different solutions to rely on. Given that ABA has the potential to affect leaf angle, and leaf angle affects light interception, photosynthesis, and overall plant architecture, this could play a critical role in crop production in the future by influencing the canopy structure, planting density, and light use efficiency. As sustainable and efficient land use is at an all-time high, this could be a promising solution for the future.